Modern civilization is synchronized by a digital heartbeat, but even the most precise machines we use to coordinate our world have a hidden vulnerability. Global financial markets rely on clocks that can account for every fraction of a second to prevent the collapse of high-frequency trading. The same invisible timing network guides global oceanic navigation, keeping ships on course across thousands of miles of open water. Our current standard, the atomic clock, tracks time by measuring the rhythmic energy jumps of electrons orbiting the outer edge of an atom. Because these electrons are located on the atom's exterior, they are constantly exposed to the environment. Even subtle magnetic fields or temperature shifts can disturb their rhythm, making our most accurate clocks surprisingly fragile. To create a more resilient timekeeper, physicists looked past those exposed outer rings, targeting the atom's core, the nucleus. Accessing it is notoriously difficult. Reorganizing its particles requires violent energy, making it nearly impossible to use for delicate timekeeping. For decades, the technical barriers to using a nucleus as a clock were so high that most physicists considered the concept a theoretical impossibility. The idea remained a fantasy until researchers identified a specific anomaly that provided a unique path into the heart of the atom. That anomaly is thorium-229, an isotope that behaves unlike almost any other element in nature. Most nuclei require massive energy to shift states, but thorium-229 is unique. Its energy levels are separated by a tiny gap. Instead of a high-energy blast, the nucleus is triggered by a gentle nudge of ultraviolet light, oscillating without being destroyed. This discovery launched a 20-year race between teams in Europe and China, each working to transform this specific atomic property into a functional tool. But proving the math was only the beginning. The challenge was to physically trap these atoms and force them to maintain a consistent tick in a real-world laboratory. Researchers finally succeeded by embedding trillions of thorium-229 atoms into a solid protective structure. They used a specialized calcium fluoride crystal to act as a cage, holding the atoms perfectly still while shielding them from outside interference. To activate the clock, a precision laser is fired into the crystal, striking the thorium nuclei, causing them to shift states at a specific frequency. To prevent the clock from losing time, physicists monitor how the light is absorbed. If the laser frequency drifts, the signal changes, allowing researchers to instantly correct the beam and lock the tick in place. This feedback loop transformed the thorium nucleus into a functioning precision instrument, the world's first nuclear clock. While these clocks are incredibly accurate, their primary purpose extends far beyond simply measuring the length of a second. Because the nucleus is so well protected from the outside world, it serves as a perfectly isolated laboratory for observing the fundamental forces of the universe. The nuclear clock acts as a high-resolution sensor, allowing scientists to look for microscopic fluctuations in the fundamental forces that hold our universe together. By monitoring these indestructible ticks, researchers can now search for evidence of dark matter or other invisible phenomena that were previously impossible to detect. These instruments may even reveal if the basic laws of physics have remained constant or if they have been subtly shifting over billions of years. Atomic clocks gave us the technology to navigate the Earth. Nuclear clocks are designed to help us navigate the unknown variables of the cosmos. The engineering race to build the clock has concluded. The scientific race to discover what it will reveal is just beginning. Subscribe to stay updated on the data these new instruments produce as they test the very foundations of our physical reality.